All right, let's jump right in. When you think about writing code, it's easy to assume that if it works, hey, job done, right? But what if I told you that the best code isn't always the fastest? Sometimes the best code is actually the one that's easiest for another person to read. You see, writing good code is this fascinating balancing act between two huge and sometimes competing ideas. It's an art, but it's also a science.
So, that really brings up the big question, doesn't it? What is the difference between code that just works and code that's truly great? Well, the answer really boils down to one simple thing. Who are you writing it for?
And Miss Slide, this captures that dilemma perfectly. On one side, you've got the humans, your teammates, the developers, who will have to read, debug, and maintain your code for years to come. For them, you need clarity, simplicity, maybe even a little bit of elegance. But on the other side, you've got the machine, the computer that's going to execute your commands 1,000,000 times a second. And for the machine, elegance is totally irrelevant. All it cares about is raw speed and efficiency. Great code, well, it manages to find that perfect sweet spot right in between.
To really see what I mean, let's walk through a real-world example. Think of it as a little story about two different ways to solve the exact same problem, with each one trying to please a different master.
Okay, so our task is pretty simple. We need to add two complex numbers using C++. Now, you might remember from math class that a complex number has two parts, a real part and an imaginary part. Our goal is just to write some code that adds them together, just like we would on a piece of paper. And this is a perfect example, really, because the math is so simple, it lets us focus entirely on the style and the structure of the code itself.
So let's start with the art. How can we make our code as clear, simple, and intuitive as possible for another programmer who comes along and has to read it?
Here's our first attempt. We've got two complex numbers, a and b. To add them, we call a function on a, and we pass b into it. Kind of like this, a.add_b. Now, don't get me wrong, this works. The computer totally gets it. It'll spit out the right answer every time. But does it feel natural to a human? Not really. It looks like a computer command, not a simple math equation.
So, how do we fix that? Well, C++ has this absolutely amazing feature called operator overloading. It basically lets us teach the plus sign what it should mean when it sees our custom complex number objects. We can literally redefine how the operator works to make the code speak our language, not just the computer's. It's kind of like a superpower.
And boom, this is the result. C equals A plus B. See? It's clean, it's beautiful, and it reads exactly like the math problem we're actually trying to solve. This is elegance. This is writing code for other people. This is the art of programming.
Okay, so we've made something beautiful. We've created code that's easy to read. We've mastered the art. But now we have to ask the really tough question. Is it fast? Because let's be honest, code that's easy to read but takes 10 seconds to load, that's a failure. It's time to shift our focus from the person to the machine.
And this is exactly where the science comes in. Elegant code is fantastic, but if it's agonizingly slow and 1,000,000 users are all hitting your app at once, it's basically useless. So the question becomes, how do we measure the performance of our code in an objective, scientific way?
Measuring performance is actually a lot trickier than you might think. There are some really common traps people fall into that give you totally misleading answers. But thankfully, there's also a standardized, correct way to do it.
So could we just time it with a stopwatch? Nope, that just tells you how fast your specific computer is, not how good your code is. What about counting the lines of code? That's no good either. I mean, a brilliant programmer might solve a problem in 10 elegant lines that takes someone else 100 messy ones. The only reliable way is to analyze how the work grows as the amount of input data gets bigger.
And this method actually has a formal name. It's called algorithm analysis. It's how we create a universal yardstick for an algorithm's performance, one that's totally independent of the hardware you're using or even the programming language. We're not measuring seconds here. We're measuring the rate of growth. And that is absolutely crucial because it helps us predict how your code will behave when it goes from serving 10 users to 10 million.
The language we use to talk about this growth is called Big O notation. If you've ever been around programmers, I guarantee you've heard them talk about something being O of n, or O of n squared. This is what they're talking about. It's the universal shorthand for how efficient an algorithm is.
What I love about Big O is how it simplifies things. The core idea is captured perfectly by this analogy. If you're buying elephants and goldfish, the total cost is pretty much just the cost of the elephants, right? The goldfish are a rounding error.
Big O does the exact same thing for our code. It tells us to ignore all the small, constant stuff and focus only on the one part that grows the fastest as our data gets bigger, the elephant in the code.
Let's look at some real code. This loop runs exactly 10,000 times. It doesn't matter what input we give the program, it always does the same amount of work. We call this O of 1, or constant time. Its performance is totally flat, it's predictable. It's like finding a book in a library when you already know its exact call number. It always takes the same amount of time.
Okay, but what if the loop runs up to n, which is the size of our input? Well, now, if we double the amount of input, the runtime roughly doubles too. The growth is a straight line. This is O of n, or linear time. It's like trying to find your friend in a single-file line. The longer the line gets, the longer it's going to take. This is super common, and often it's perfectly fine.
But now, look what happens when we put a loop inside another loop, and they both go up to n. This is where things get scary. For every single item, we have to process every other item. The workload doesn't just double, it squares. This is O of n squared, or quadratic time. For small inputs, no big deal. But for large inputs, this is how websites crash. This is the performance killer you have to watch out for.
And finally, check this one out. Instead of counting up by 1, our counter I doubles each time. It goes 1, 2, 4, 8, 16. It gets to a huge number n incredibly fast. This is like finding a name in a phone book. You open to the middle, and you instantly throw away half the pages. This is O of log n, or logarithmic time, and it is phenomenally efficient. This is the holy grail.
And this chart just shows you how dramatic the difference is. Look at that. With an input of, say, 100 items, the logarithmic algorithm is barely working. The linear one is manageable, but the quadratic one, it's already exploding off the chart. That steep curve for O of n squared is the difference between an app that feels instant and one that makes you want to throw your phone against the wall. This is the science of performance.
So this brings us all the way back to where we started. This constant push and pull, this dilemma between making code beautiful and clear for people and making it blazingly fast for machines.
And here's the real takeaway. Good software development is a constant negotiation. It's about knowing when to pick the elegant, readable solution that's going to save your team time and headaches, and when you absolutely must choose the more complex but hyper-efficient algorithm that can handle a tidal wave of data. It's all about finding that perfect balance between the art and the science.
And that leaves us with the ultimate question that every single developer has to face probably every day. When you have to make a choice, when there's a trade-off, which do you prioritize? Simplicity for the next human who has to read your work, or raw speed for the machine that has to execute it? The answer? Well, that's what separates the good programmers from the truly great ones.